In a previous video we established the fundamentals of practical digital signature schemes. One of the first such schemes was RSA. It was proposed in 1978 by Ronald Rivest, Adi Shamir, and Leonard Adleman, and it is still relevant today. Its construction relies on cryptographic primitives called trapdoor permutations and cryptographic hash functions. In the following we will derive the construction of the scheme step by step. A family of trapdoor permutations is a cryptographic primitive that augments the concept of a permutation function with some additional useful properties. Firstly, it provides a way to sample an instance from the family given a random seed S. Such an instance consists of a permutation function, f, and a trapdoor function, denoted as the inverse of f. The permutation function maps inputs from some fixed domain onto elements of the same domain with a one-to-one mapping. The trapdoor function is the inverse of the permutation function. In general, it is not clear that given an efficient algorithm for computing the permutation, it is also easy to compute its inverse. For a trapdoor permutation, we require that on average it is computationally infeasible to invert the permutation without knowing the trapdoor function. In 1976, Whitfield Diffie and Martin Hellman proposed a digital signature scheme that is based on a trapdoor permutation family and works as follows. For key generation, sample a trapdoor permutation instance using the random seed input. Then, define the trapdoor function as the private signing key, and the permutation function as the public identifier. For signing a message, apply the trapdoor function to the message and define the output as the signature. Note that this only works for messages from the domain of the trapdoor function. Also note that nobody without the trapdoor information will be able to do this, which hints that the scheme provides some protection against signature forgeries. For verifying the authenticity of a message against a given identifier, interpret the identifier as the permutation function, apply the permutation function to the signature, and compare the result to the given message. If both values are equal, the signature counts as valid. Having proposed the scheme, Diffie and Hellman, however, left open the question whether a trapdoor permutation family actually exists. In 1978, Ronald Rivest, Adi Shamir, and Leonard Adleman propose a concrete trapdoor permutation family, which is commonly referred to by RSA. Their construction works as follows. For sampling a trapdoor permutation instance, first choose two large prime numbers, p and q, for example of size 2048-bit. Then, define n as the product of p and q, and phi as the product of p-1 and q-1. Now, choose a value, e, that is co-prime to phi and compute d as the inverse of e modulo phi. The value d will be used as the trapdoor secret, and n and e will be the public information defining the permutation function. The permutation function, f, is defined over the integers modulo n. On input an integer x between 0 and n-1, the function computes x to the power of e modulo n and outputs that value. The fact that e is co-prime to phi ensures that f is a permutation function. This permutation function is assumed very hard to invert without knowing the trapdoor information d, and it has proven to be so in practice. In fact, you can win a considerable amount of prize money if you can solve one of the RSA challenges. None of the RSA challenges for n larger than 829-bit have been solved at the time of producing this video. However, if the trapdoor information, d, is known, inverting f becomes easy. Given an integer y between 0 and n-1, the trapdoor function is computed by taking y to the power of d modulo n. An interesting side fact is that there is a relation between solving RSA challenges and integer factorization. If we could factor the public value n into its prime factors p and q, then we could derive the secret trapdoor information d. This shows that solving RSA challenges is at most as hard as factoring integers. The Trapdoor signature scheme instantiated with the RSA Trapdoor family has the following properties. Signing and verifying messages is relatively fast. Signing is done in time less than cubic in the size of the public key, and verification is done in time less than quadratic. However, keys and signatures have the same size as the signed data and are therefore not small. Moreover, signatures are forgeable due to the multiplicative structure of the RSA Trapdoor function. By multiplying two signatures we obtain a signature for the multiplication of the messages even though this message was never signed. In the next section, we will have a look at how we can improve upon signature size and security by using a cryptographic hash function. A cryptographic hash function is a function with the following properties. Firstly, it is a compression function, which means that it deterministically maps inputs of some size m to outputs of a shorter size n. Secondly, it must be hard to find collisions of the function, that is, two different inputs that map to the same output. Thirdly, the hash function must behave like a random function. On average, it must be infeasible to distinguish the hash function from a randomly chosen function with the same input and output domain. By combining a trapdoor permutation family with a cryptographic hash function, we obtain a relatively secure and efficient digital signature scheme, as follows. For key generation, draw a trapdoor permutation instance and select a cryptographic hash function whose output domain matches the input domain of the trapdoor permutation. For signing a message, first hash the message and then apply the trapdoor function to the hash value. Define the output of the trapdoor function as the signature. For verification, apply the permutation function to the signature and the hash function to the message. The signature is valid if the two values are equal. The hash and sign signature scheme used with the RSA trapdoor function and a popular hash function such as SHA-256 is relatively close to the RSA signature scheme that we use in practice, and it has the following properties. Signature generation and verification is still fast because applying hash operations is relatively fast compared to evaluating RSA. Signatures are now constant size because messages are first hashed and thereby compressed. The security of the scheme is also improved because the application of the hash function destroys the multiplicative structure of the RSA function. However, so far security of the scheme could not be proven based on standard assumptions but only when viewing the hash function as an unrealistically perfect random object. This concludes the end of this video. I hope you could take away some basic concepts of building secure and efficient digital signature schemes. In the next videos, we might explore how we can further improve security and efficiency or investigate other schemes with additional properties. I hope to talk to many of you then again.